Good afternoon, everyone. I'm Aaron Imani, a PhD candidate at UC Irvine. In this talk, I'll walk you through how we investigated the existence and role of comments in large language models representation space, as well as their impact and sensitivity to downstream tasks. Code comments are used in software engineering tasks, such as bug fixing and identifying self-admitted technical debts, among many others. Over the past few years, large language models have been increasingly adopted to automate software engineering tasks. So researchers have investigated the effect of comments on large language models' performance as well. Depending on the task, comments can help, have no effect, or actually hurt LLM's performance. So we're left with a mix of effects and no clear explanation for why comments affect tasks in these different ways. We also know LLMs don't simply react to prompt tokens. Their behavior is driven by human understandable concepts that are encoded in their internal representation space. For example, one such concept is prompt safety, deciding if an input is malicious or safe. Researchers have shown that LLMs have learned prompt safety as a concept, and manipulating this concept inside the model's representation space outperforms traditional jailbreaking methods that focused only on the prompt. This leads to the high-level question behind this work. Do LLMs internally recognize comments as a distinct concept? To really get at this, we split this big question into four targeted research questions. Specifically, we aim to investigate the internalization of comments, its different types, and the impact of this internalization on downstream tasks, as well as the task dependency of the activation of comment concepts in large language models. I'll go into more details regarding each research question in the upcoming slides. To conduct our experiments, we focus on the Java programming language because of its popularity among developers and its wide adoption in software engineering literature. To minimize the confounding factors such as differences in training data distribution, we picked the subject LLMs from the same model family, Qwen 2.532 billion. However, to help with generalization, we selected three different variants of this family, namely a code LLM, a generic instruction-tuned LLM, and a reasoning LLM. To investigate the existence of comments as concepts in large language models representation space, we adopted linear interpretability. First, we had to define our concept, which in our case is different types of comments in Java code, namely inline, multiline, and Javadocs. Next, we built a contrastive dataset designed for this concept from top 10 Apache repositories. These pairs consist of positive case, which is a piece of code with comments, and a negative case, which is the same code with no comments. Given the contrastive dataset built from our concept, the next step was to train a linear classifier that classifies the subject model's embedding from the dataset. We say the concept is internalized by the model if the classifier's accuracy is high. Consider this square as a representation space of an LLM, where the gray circles represent the embedding of negative examples and green triangles show positive examples. In this setting, since these two sets are cleanly separable using a linear classifier, we say the concept is internalized. But if the examples look like this in the internal representation space, there is no linear classifier that can separate them with a high accuracy. Therefore, the concept is not internalized. Regarding the linear classifier, we adopted logistic regression from the literature. We trained it on every layer of each LLM, and we used the embedding vector of the last token of the code as the input to these classifiers because it captures the embedding of the entire sequence thanks to the causal language modeling in large language models. For example, this single line of code in Java, the information flows from all tokens to the semicolon token that accumulates the sequence information. To answer our first research question, we measured the median accuracy of the classifiers across the layers of the three LLMs. The accuracy ranged from 88% to 99% using 5 different training split sizes. So the answer to our first research question is LLMs internally encode comments as a distinct concept, differentiating between different comment types. We chose 3 tasks to assess the impact of comment concepts. That includes code completion, translating code from Java to 4 other programming languages, and code refinement. To assess the significance of internalized comment concepts, we first established a baseline performance by running LLMs on each benchmark with and without comments. But these 2 baselines do not tell us the impact of concepts because they only vary in the input level. We needed a method to control and measure the influence of these concepts internally on the behavior of LLMs. This led us to use the concept activation vector or CAV methodology proposed by Kim et al. Given a positive set and a negative set, assume we have a linear classifier that separates them with a high accuracy. If we draw a perpendicular vector to the linear classifier, we have a direction vector towards the embedding space that belongs to the concept of interest. This vector is called a CAV. CAV enables us to perturb the embedding of any code towards or against the direction of comment concepts. We assess the significance of internalized comment concepts from 2 perspectives. First, we analyze if the impact of comments solely comes from their internalization. To do this, we activated the comment concepts based on CAV on the comment-free code. We call this experiment concept activation. Second, we answered the question, would comments be helpful if we suppress their concept internally? To do this, we deactivated the comment concepts on code with comments. We dubbed this experiment concept deactivation. Here we can see the summary of the changes in the performance of LLMs on each downstream task. Both activating and deactivating comment concepts hurt LLMs on code completion and refinement tasks. But for code translation, we observed a performance boost. This suggests that overall, LLMs have developed a strong internal reliance on comment concepts. When we perturb these concepts, either by forcing them on or suppressing them, the impact is usually negative. To examine task dependency, we merged all the samples from our 3 benchmarks in research question 3 to gain a consistent set of code across several tasks. Then, we picked 10 different software engineering tasks to cover a range of code-related scenarios. To measure the sensitivity of concept activation to tasks, we used the mean prediction probability of classifiers for each concept averaged across all layers of LLMs. Our findings show that the strongest task-dependent activation of comment concepts occurs in code summarization, while comment concepts showed the weakest dependency on code completion. Our study leaves open questions for future work. In research question 3, we observed positive and negative impacts of comment concepts when perturbing them across tasks. However, what is yet to be answered is when exactly do internalized comments harm performance, and what causes comments to boost performance in some scenarios but hinders it in others. This wraps up my presentation. I had to skip details about our methodology and fine-grained results in favor of time. If you got curious about them, please feel free to give our paper a read. Thank you for attending my talk, and if you have any questions about our work, please feel free to scan the QR code to my LinkedIn, send a connection request, and send me a message there. Thank you so much for your attention.